Yeah, okay, so you were asking about gravity?
Yeah.
Yeah, gravity, as
Mhm.
described by most people as mass
Mhm.
attracting mass or space-time, right? One of those two things, they're to do with the globe. Okay, so you guys need to be able to explain your model. You need to be able to explain how you can have oceans sticking to the outside of a ball and that kind of thing. Okay, and how we can have gas pressure here on the Earth next to a big giant space vacuum without all of the gas, filling the available space of the vacuum. A whole bunch of reasons. Why don't you float off into space? How can we have water inside this big space vacuum? All these kinds of things. You guys need to have something to be able to explain all of these things that kind of defy what I would call logic and common sense and practical demonstration. So to have a globe, you have to have gravity, and to have gravity, you kind of have to have the globe as well. So it's something
So
that's globe dependent. In reality, okay, in a flat, stationary, enclosed system,
mhm.
we don't need to have gravity in the same way that it would be necessary if the Earth were a globe.
So how does it work?
Well, it's very easy. It's very simple to explain as well. So if something is more dense than the air,
Mhm.
then it's going to sink through the air. And if something's less dense than the air, it's going to rise, right? It's going to go up. Like a helium balloon, for example, it's less dense than air, and it's going to go upward if you let go of a helium balloon. But if it was more dense than the air, it's going to sink downward because the air is a very light medium, so it doesn't have anything to support it. So if you drop a rock or something like that, it's just going to sink back to where you picked it up from, which is just downward.
Like what's causing it to go downwards? Because when I drop something, the air is
Hmm.
all around it. Why it's not
Yeah,
going
yeah.
like up
Well,
or
it's
down?
it's because you picked it up. It was already down, and it never would have moved. Right? That whatever you picked up, it would have just stayed there unless some outside force actually forces it out of its state of rest. So it's only going to drop because you picked it up, okay? And you've given it potential energy, you've displaced it, and it's going to reseek equilibrium based on its density.
So I gave it potential energy, which causes it to increase the energy.
No,
Since you're
you've
taking the
displaced it.
example, since you're
Yeah.
comparing it to equilibrium state, as I
Yeah.
understand with equilibrium state, when a system or object is moved from its equilibrium state, it tries to get back to its equilibrium state. Okay, for example, a
Yeah.
spring, when you stretch a spring, like when you stretch a spring and put potential energy into it, just like I picked up the stone and increased its potential energy, so the spring applies a force on itself to decrease that potential energy and get back to its equilibrium state. So in that context of stone, what's applying
Definitely.
the
We'll do it in
force?
a
Like
minute.
what's the force that's being applied on the rock? Like in context of gravity, I could say the gravity is applying the force, but I wouldn't understand would I say as a flat earther, you know?
Well, it's as using a spring as an example is just a false analogy, right? That's just one object. Okay,
But both
and
are the examples of equilibrium state and potential energy. Why is it a false analogy? Analogy.
well, it's a false analogy. It doesn't compare. You could use the equilibrium state for different examples that aren't analogous to each other, like the spring. This is something falling through a medium. Okay, and we
Hmm.
this is what we can do. Okay, we can test this. Let's say we get an egg, and then we have a cup of water, fresh water.
Hmm.
Okay, and then
Hmm.
we put the egg in the water. The egg's going to sink down to the bottom of the cup. Now, we can vary and manipulate the medium by changing the density of the medium. Now, that's the water. Now, if we
Hmm.
add salt to the water,
Hmm. Hmm.
okay, now the egg is going to go upward. The egg went downward, and now all we've done is vary and manipulate the medium, and now all of a sudden the egg's going to go upward. Nothing's touching it, nothing's forcing it. All you're doing is changing the medium, and then the object will behave differently.
So
That's the
what
only
is
thing.
density exactly? It's mass upon volume, right?
Well, no, I would say that the density is simply what the object is made out of. Okay, so whatever natural elements the object is comprised of is going to be what I would consider the density of the object.
How do you calculate the density of an object? Like by science, I would say we'll calculate the mass and then its volume, and then we'll divide these things like mass upon volume, and then we'll get the density. Is that not right?
Well, just depends. I mean, you can do it any way that you choose to do it. I mean, if you have a ball of lead, okay, it's just a ball of lead. So you can try to calculate the density all you like, but it's just a ball of lead. I'm not trying to calculate the density of things. So I'm not needing to calculate the density of things. I'm just showing you
No, I'm not denying
why
on the
things are going to go.
observation that we are experiencing. I agree with
Yeah.
that, but I don't understand why it's happening. For example, as you said, the egg is denser than the water, so it's going down, right?
Yeah.
Density of egg is higher than density of water,
Correct.
and that difference in density is making it go down. But why? Like
Because it was
that
lifted
question.
because it was lifted up and
But
placed into
what
that
force is being applied on it? As
the
like we
force.
know, the, the
Yeah, so
thing won't move unless we expand.
the force
Okay.
that displaced the object is what's being applied on the object, right? Like put it like this, right? Let's say I get a tennis ball and I have
Hmm.
a fish tank of water.
Hmm. Hmm.
Okay, and just say there's like a ledge inside the fish tank under the water, and I push the tennis ball down under the ledge.
Hmm.
Okay, now the tennis ball is under the ledge. I've forced it down there. That tennis ball has potential energy, right? And as soon as that tennis ball comes out from under that ledge, it's going to come back up to reseek equilibrium. It could stay down there for a week. Okay,
Well,
it's still that
no,
initial force. It's still that initial force that I applied to it to
but I
push
can
it down
explain the
there.
force that's being applied for it to go up.
Yeah, it's the buoyant. It's because of the buoyancy.
Yeah, it's because of the buoyant force. The
Yeah,
water is
but
trying to go down, but
the only reason it's going to happen, the only reason it's displaced is because I forced it down there in the first place.
well, still, for it to come up again, there should
Yeah.
be a force that should be applied on it to make it move from down to up after you left your hand and the ball is down in the aquarium or sink.
No, the initial force is the cause, right, of the
So are
potential
we
energy
saying
that the
something
ball
is
has.
moving without a force required for it to move,
Okay, so what do
like
you think's pushing? What do you
Newton's?
think's pushing? Do you think gravity is pushing the tennis ball upward through the water?
No, the thing I
Obviously
understand is
not.
this is what's happening there. So the water has more density than the tennis ball. Okay, so the
Hmm.
gravity is pulling water down. The gravity is pulling water down where the ball is with the lesser density. So the water will try to push it up so that it could go down, and this is
Right.
called buoyant force.
Yeah, yeah. On a
That's why it's
globe,
being pushed up.
if the Earth were a globe, then sure, you would need to have that buoyant force that has gravity in the equation. But in reality, we don't have a globe, and we don't have gravity, and we can easily debunk gravity. Easily.
But really, your explanation is going against basic laws of motion, Newton's laws of motion.
No, it's not going against laws of motion. It's going against the globe claims. It's going against the globe theory that claims gravity, that claims mass attracting mass, that claims a downward force or pseudo force. That's what it's going against.
Downward force
It's
is
going against
pulling.
pseudoscience. It's going against pseudoscience is what it's going against. And we can easily debunk mass attracting mass. We can easily debunk that. That's been done thousands of times.
Okay, so according to Second's laws of motion, as far as I
Yep.
understand, at any instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equal to the rate at which the body's momentum is changing in time, right? So there should be a force applied on the ball for it to accelerate from the rest state, which is down, to coming back up. What is that force? Is what I'm trying
The
to
force, the
understand.
potential energy was the initial
Potential
force that
energy
displaced the object.
is
Yeah,
potential energy
potential
and
energy.
energy.
It's
It's
the
an
same thing
energy.
with the spring. Yeah, it's the only reason that the spring is going to move is because you
But
pushed the spring down and compressed the spring.
but
If
in
you didn't
case of
apply that
spring,
if you
there's a
didn't
force
apply
being
the
applied.
initial force. Yeah, so there's an easy way we can just debunk this whole
Mhm.
globe and gravity. Okay, so
Uh,
would you agree? Okay, so
mhm.
let's just debunk it really quickly.
Mhm. Mhm.
Okay, so gravity is pulling everything towards the center of the globe, right?
Yeah.
Okay, so that would mean that the water that covers over 70% of the globe would have to be curving at a specific rate because of gravity.
Mhm.
Yeah, so if you
Okay.
have a large body of water like a lake, for
Mhm.
example, then
Mhm.
it has to be curving at a certain rate, and we can calculate how much the water would be curving over a certain distance based off the radius of the Earth. Do you agree?
Uh-huh.
Okay, so if that water is not curving, that would debunk the theory of mass attracting mass and everything being pulled towards the center of a globe. It would have to be happening if the Earth were a globe, right?
And how would you test that water is not curving?
Very easily.
Hmm.
There would be certain characteristics that would be visible over the surface of the water, right? That we can check very easily. Okay, because we have high-powered lasers, we have high-powered optics, zoom cameras, telescopes, radio wave signals, all sorts of light propagation, wave
But how
propagation
exactly?
technology. Okay, so firstly, just a simple observation. Okay, so
Hmm.
we could find a 10-mile body of water, and then we could set up a camera, a high-powered
Hmm.
zoom camera on one side of the body of water at a certain height. Let's say 1 meter high,
Hmm.
and then we could have a target on the other side of the body of water,
Okay.
say 1 meter high. Okay, and if there's curvature there, okay, we can calculate that over that 10-mile distance, there would be 66.7 feet of curvature, which is about 22 meters of curvature. Okay, so you shouldn't be able to zoom in across that body of water with your camera and
The thing
see.
you're saying is that we can't see far after the curvature, right? Is that what you're saying?
Yeah, so
Okay.
what you should see is
Hmm.
you can calculate the distance to how far the cutoff point is, which would be called the horizon. Okay, so the horizon would be at a certain distance based off the height of the observer.
Hmm.
So if you have a 1 meter high observer, the horizon would be at 2.3 miles away, which is
Hmm.
about 3.4 kilometers, I think.
Well, that's assuming Earth is a perfect square, right? Earth is not a perfect square, even in theory.
Yeah, but it would be approximately 2.3 miles, maybe
Approximately.
2.3. Yeah, so
Mm-hmm.
The Earth is so close to being a perfect sphere. You know, like it's basically a perfect sphere, except technically it's slightly off. So they call it an oblate spheroid, but it's only 0.33% off being a perfect sphere. So it's only a tiny little bit wider at the equator than the poles. Overall, right, on a grand scale, the drop over distance formula doesn't change
Mm-hmm.
enough that they even take that into consideration.
Mm-hmm.
So it's going to be approximately 2.3 miles from a 1 meter observation height anywhere on the Earth at any altitude on the Earth. It might
Mm-hmm.
change by like 1 point or something like that, 1 or 2 points, but it's just a point. Like it's not much, not enough to take into consideration.
Mm-hmm.
For example, if you take NASA's pictures of the Earth that they claim,
Eh,
and you put
okay.
a perfect circle around them in Photoshop, it fits. But anyway, so we can do this
Mm-hmm.
observation, and we've done this observation over and over and over again. It's like it's been done probably thousands of times now. And we can not only see a little bit further than what we should be able to see on the globe, we can see only flatness, and we can see many thousands of percent further. Okay, so that water is not, absolutely not curving, and there's absolutely no evidence throughout all of history that the water is curving. No evidence that that's empirical. Maybe faith-based evidence if you want to trust NASA, for example, but that's not something you're going to be able to test. You're gonna have to take their word for it. But when we
But
test it in reality, there's no curvature. The water's not curving, and if the water's not curving, then the theory of mass
uh,
attracting mass or the bending and warping of space-time fabric, these theories are just theories. They're just concepts.
so
They're
even
not.
after like I believe that Earth is not curving, the world is not curving,
Mhm.
that still doesn't explain why the stone is going down or the ball is going up. Like
Yeah, it
I
it
understand
does.
there's potential energy in the ball now or in the stone, but what's the force that's being applied to the stone to get go for me to for making it go down?
It's the initial
Uh,
force that's the displacing force.
yeah, the initial force was me pushing it upwards, like pulling it upwards, right?
Yeah.
That made the stone left the ground. Okay, so when
Yep.
I stop applying that force, it should stay there.
No, it will sink because it's more dense than the medium.
And what's the force being applied on it?
You applied the force on it to displace
But
it.
I'm not applying a force on it anymore.
Yeah, so it's got its own density. So it's able to
Density is a
it's able
property,
to
it's not a
sink.
force.
That's the property of the object. Okay, so the
Mm,
property of the object means that it's more dense than the surrounding medium, so it cannot
mm-hmm.
be supported. It can't be supported by the surrounding medium, so it's going to sink through it. This is Archimedes' principle. It's
But
called specific.
why
It's
is
called
it going
specific
down
gravity.
though?
Archimedes came
Okay,
up with this. Have you not heard of Archimedes' principle?
I have heard of it. Again, as you said, I'm trying to understand here. Okay, the stone is surrounded by a lesser, denser medium,
Mhm.
but it's also upwards, right side and left side. Why is it
Yeah.
going down?
Why would it not go down? That's where you picked it up from. It never would have moved from where it originated unless something displaces it.
But like
It
there
has
should be
it
a
has an
force that's
original it has
being.
an original place. It has an original place of rest, right?
That's
Like
cool.
a
That's
rock.
fine. That's fine.
Yeah.
But as I said, according to second law of Newton's laws of motion, a
Mhm.
body should only accelerate when there's a force being applied to it. I'm asking what's the force that's being applied to it when
You've
it's
applied
accelerating
you
downwards. No,
Yep.
you don't understand. I think
You've
I'm
applied the
unable to.
force. Well,
Yes, I applied the
this is the
force.
thing. This is the thing. This is
Hmm.
what it comes down to.
Hmm.
Okay? You can just test. You can test what I'm claiming over and over again.
What
Okay? If
is
if you're
going to?
claiming, okay, so what do
Okay.
you think? Let's switch it over to you. Okay,
Hmm.
this is what it comes down to. Why is down
Hmm.
down? Why is down down? And why is up up? Is that what you're really asking? Why are there two primary directions that things go?
No, I didn't ask that.
Okay, well that's what you're talking about. Why is it going down and not going up?
Well, as for because of your explanation, you're saying that it's surrounded by a low
Yeah, so
denser medium.
there are two primary directions. Do you agree with that?
You're just mocking me at this point.
No, no, no. There are two primary directions. You can test this very easily. If you drop something, it goes straight down, right?
Hmm.
If you have something that's less dense than the air, it goes straight up. It's never going to
Hmm.
do anything other than go straight up or straight down if there's no
Hmm.
extra forces at play. How is that mocking you? That's something that anyone can test. Okay, so if you have a incense, a stick of
Hmm.
incense, and you put it in a room and there's no breeze.
Hmm.
Okay, that smoke, what direction's the smoke going to go? Up. It's
Hmm.
going to go up
Up.
in a perfect straight line up. Okay, and
Okay.
if you drop something, let's say I'm in that same room and I pick something up and I drop it, which directions is it's going to go straight down in a perfect line, straight down.
Hmm.
Okay, that means that there's two primary directions, up and down.
I'm not denying that. Yeah, there are.
Well, you just said I was mocking you for suggesting it, but
No,
now you
like
agree.
you don't have to explain me directions. Is what I was trying to say.
Yeah, but we need to try to get to the bottom of this. Okay, so obviously
Fair, fair,
something's
fair.
something's going to go up or it's going to go down, right? It's not going to go any other direction.
Okay, so
Okay, so you're
okay.
asking me why is up up and why is down down. That's what you're
No, I'm
asking.
saying I'm asking why it's going down. I'm
Yeah,
not
so why
asking
is
why
down
down
down?
is down. I'm asking why it's going down, the why the stone is going down. I understand there's a difference in density between the stone and the
Yeah, but
air that's below it.
you're asking it assuming that you live on a globe and that you need to have a force because you
No, no,
there's
no.
yeah, because you're in space. You're thinking that you're in space, in a big giant space vacuum.
We, don't you think we have to have force for something to move?
You forced it. You applied the force. That's the only reason it moved. It never would have moved without you applying the force to it.
Do you know what? Do you know the three laws of motions that were introduced by Newton back in the days?
Mhm. Yes.
First is law of inertia, that one thing won't move unless there's a force being applied to it. A body remains at rest or in the constant speed in straight line unless it is acted upon by a force, right?
Mhm.
So when there's a stone at rest on the ground, I applied a force on it for it to make it move upwards up to a certain
Yeah.
height.
Yep.
For it to move upwards, I had to apply a force on it, right? Okay, now second laws of motion states that an instant of time, the net force on a body is equal to the body's acceleration multiplied by its mass, or equivalent the rate at which the body's momentum is changing with time. Is that true or like not?
No, I think mass is a convoluted term, to be honest. Okay, yeah. Look, let's just get straight to the heart
Hmm.
of the issue.
Hmm.
You're claiming gravity exists and that's the reason, right?
No,
You're
I'm not
claiming
claiming anything.
gravity.
I was saying
Yeah, you
the
are.
actually the thing that
Okay,
happened
so
was
do you
yesterday I
believe?
was in a debate with says who he was sitting
Mhm.
in this VC.
Yeah.
So I was talking to him and I wanted to read more about it. So I asked him if there's a resource or something that I could look into. So he shared me a Discord link and it had ton of videos and articles. So I looked into it and as a truther, I would say. I looked at the arguments that contradicts that beliefs or claims. So while I was looking at it, that why Earth could not be a flat surface,
Mhm.
um, gravity was the first thing that people mentioned. So to explain that, I was thinking what could explain that, but I couldn't come up with anything because
Archimedes' principle. So if we're not we don't claim the Earth is a disk in space. Okay, we're not in space. We're not in a big space vacuum that doesn't have any specific directions. Okay, we're in a contained system where the Earth is the floor and the sky is the ceiling. Okay, we're in an enclosed system. There's only two directions, two primary directions, up and down. Okay, nobody knows why up is up or why down is down, but we can very easily demonstrate that things that are more dense than the surrounding medium will sink through them, and things that are less dense will rise. Okay, we don't need any magical force, mass attracting mass. That's a globe thing. Okay, and we debunked that easily doing countless amounts of long distance observations, laser transit tests, radio wave propagation tests, infrared photography of all distances. Okay, showing that there's no
uh,
curvature. There's no curvature of the Earth. Okay, so when we go out and we do empirical evidence, all of your theoretical concepts, your mathematical constructs, these things, these pseudoscientific theories, they don't hold any weight against real world empirical evidence that's testable, repeatable by anyone. You could go and do this yourself. So
understand that.
you can parrot textbooks all you like. Memorization and regurgitation of indoctrination is not really going to help you in this argument. So you can be really good at memorizing and regurgitating textbooks. Books are bullshit in many cases. Okay, but
Archimedes' principle was
if
part of what we read in textbooks.
yeah, so Archimedes, yeah, that's why I said some. I didn't say all textbooks, did I?
And again, Archimedes' principle won't work without the force of gravity.
Oh, really? There's no G, right? There's no gravity in Archimedes' principle. No, there was no concept of gravity when he.
Why do you think the water that's down has more pressure than the water
Why
that's
do you
up?
think the water is flat? That's the question. If gravity is real, okay, we can go and
It's
test
flat
it.
on a smaller scale is what I think.
No, it's flat on any scale, as far as we can test. Okay, so I can show you a test right now that shows you that there's
Let's
hundreds of
come back to a
feet.
smaller scale. Let's get back to
No, no,
stone first because I am still not convinced, or I could say I'm still not understanding why the stone is going down.
yeah.
You
Why
said
is down
ultimately
down? Okay, so
no,
just a moment ago, I said that there's two primary directions. Okay, you agreed with me. Okay, and then I said nobody knows why down is down and why up is up. Okay, when I drop something, why doesn't it go up? Why doesn't it stay still? Or why does it go down? Okay, nobody knows why there's two primary directions. Okay, down is down for every single person on the earth. Up is up for every single person on the earth, and it's the same direction. Someone in Australia can point up and someone in India can point up. They're both pointing the exact same direction. They're not pointing away from each other like you would be on a globe. Okay, so there's two primary directions. We have up and down. Nobody knows why down is down and why up is up, but we can easily do scientific experiments and show cause and effect relationship, showing that there's a density relationship with the medium and a displacement effect that causes things to rise or sink. That can be demonstrated over and over again. Okay, now what you're suggesting is something that requires the Earth to be a globe. It requires the water to be curving, and it requires a force of gravity.
What's your point
Those,
exactly?
my point is that those things can have been debunked because we've gone out and tested the Earth over and over again over distances where there should be a huge amount of curvature, and there's never any curvature present. If there's no curvature present, the Earth cannot be a globe. That's
okay,
the one
so
thing.
my internet got disconnected for a second. What were you saying?
Yeah, so if there's no curvature, the Earth can't be a globe. It's very simple.
It could still be a spear.
So what's
No,
the
no, you can't. Well, hold on a second. I'll just answer this
okay.
person's question. Okay, so it cannot be a sphere. If 70% of the surface of the sphere is claimed to be covered in water, and the water is all flat, then you can't have a sphere. If someone wants to try to draw me a picture of a sphere that has 70% of the surface covered in flat water, go ahead. I'd like to see what that artwork looks like. Go ahead, RK.
So what's the if the second principle of Newton's laws of motion is wrong, then what's the correct one?
I didn't. I don't. I'm falsification. No, I'm not even claiming they're entirely wrong. I just claimed how things work. Anyone can test and demonstrate and repeat
But
what
do you
I've claimed
believe
here
that
today.
Newton's laws of motions are right? Newtonian mechanics, is it right or not?
Okay, well, okay, I don't know. Let's put it to the test. Does it mean the water should be curving?
It just
Let me
meant
ask
three
you.
simple things.
No, let me ask you. Does it mean the water should be curving? Yeah, most of the surface of the Earth is covered in water. So do Newton's laws mean that the water should be curving?
Why are we going back to water is not curving thing again and again?
Well,
I'm
that's what
asking a
this
simple
is. Okay,
question.
so you know what because that's what this argument is about. This is about whether the water is curving or not curving. Because
Mm,
that's
mm,
what's required. Okay, so this is a flat Earth debate.
I understand that, but my
Okay,
question
so
was
you believe
simple.
the Earth's a globe, and that requires the water to be curving. And if you want to claim gravity, then you need to have curving water. Okay, and
You
I can
don't
prove to you.
have curving water.
Can you? I understand that what's as I said, if I believe what you're saying is true, and I want to believe that, okay,
Mhm.
what would cause the stone to fall down is what I'm asking.
I
And
already
you're just
explained it. I
going
already
back
explained it.
to
Yeah, I
the
already
down is down and up is up.
Yeah, I already explained that it was displaced and then it's simply sinking by its own what it's made of. Its own density is causing it to sink through the medium only
And
because
then
you lift it up.
again, that's against the Newton's laws of motion.
Okay, well, if you're claiming that that's going against Newton's laws of motion, then that's
Mm.
wrong, isn't it?
Who says Newton's right?
So
Newton didn't even
Huh?
say Newton was right. Newton said that he was anyone that believes in his theory of gravity
Exactly.
lacks.
So are you saying Newton's laws of motions are
I didn't say
wrong?
anything about Newton. I didn't say anything about Newton. You
So
seem to
if
be
they are not
obsessed
right,
with
if they are
Newton.
not wrong, then what they are? What are they?
I don't care.
It's just at the end of the day, it's still a theory.
Yeah, I
It's
don't
not
care
theory.
about Newton or Newton's laws. Okay, we go and test the Earth.
So we don't care about physics anymore.
No, I care about physics. I don't care about Newton's laws right now because we've gone out and tested the Earth and it's not curving. So whatever you think.
Archimedes' principles also uses laws of motion. You know that, right?
Okay, that's great. Things move.
Good
The
for
water's
you.
not curving. You don't even want to see the tests. You're not interested in the truth. You're trying to get a little gotcha or something like that.
I'm just trying to understand it better.
Okay, so if the water is not curving, the Earth is not a globe.
Okay, it's not a globe. It's not a globe, okay? I
Okay.
agree with you there. It's not a globe.
All right, well, that's it. That we're done here.
No, we're not done. I still want to understand other phenomena like stone falling downwards or other things.
Yeah, I told you why
It's easy.
something falls down. I told you why something falls down.
Mm.
You didn't like the answer.
No, it's like against the basic physics is what I'm saying.
Oh, okay.
We do believe in physics though, right? Even though
Yeah, like the
I
physics of
agree
water.
that Earth is
The
flat.
physics of like the physics of water, for example, fluid dynamics.
You just mentioned Archimedes' principle is the reason that the ball is going up or down.
No, I
in the
told you
water or air.
exactly. I told you exactly what it was. It was because it was displaced because the density is higher than the density of the surrounding medium. That's the reason. You don't like it because you've learned something else.
No.
Okay,
Let me just see.
this is.
It's not that I don't like it.
It is because you don't like it. This is your.
Let me just say.
You're coping
Let
right
me just
now.
say.
Is what you're doing.
No, it's not. Okay.
It is.
So you said that
Yep.
the difference between the density is causing the movement of stone from up to down, right?
Yep. No, I said the cause is whatever the energy was that displaced or forced the rock out of equilibrium. Okay, and then it's simply going to reseek equilibrium due to the density
Without
of
any
the rock.
force on it.
The
Like there's
force
no
was,
force being applied on it, right?
the force was already applied. Yeah, there was a force applied.
Well, that's against just basic physics. How do I explain
Oh,
that?
okay. Well, your basic physics that you're talking about thinks that the Earth is a globe, right? And that water's bending around a ball that's spinning at millions of miles per hour
For
through outer
real.
space. Cool. So yeah, maybe your textbooks are just information that you've learned how to regurgitate, and you think that makes you smart because you're able to parrot information that you learned.
Is there a research paper or something that I could read about the density difference? That's causing?
Go read up on Archimedes' principle.
Archimedes' principle requires Newton's laws of motion, and your
No,
theory
it
is
doesn't.
directly going
It
against.
doesn't.
It does.
No, it doesn't have anything to do with anything about Newton. Okay, so he's from BC.
Okay.
Archimedes is from BC. Okay, do you think he was writing anything of Newton?
So do you think that knowledge doesn't carry forward to the future? Okay, let me just. Should I screen share? Can I screen share?
Mm-mm.
Okay.
Nobody can screen share.
Oh shit! Okay. The Archimedes principle that explains the buoyancy force, right? Right. The
Yes.
formula of it is force of buoyancy is equals to rho g and v. That's rho is density of the fluid.
G? What's the G?
G is acceleration due to gravity.
No, gravity. Okay, that's not in the original Archimedes principle formulas. It's not there. Okay, because this guy was from the BC. He didn't believe in gravity. Newton didn't exist then. Okay, remember Newton discovered gravity when the apple fell on his head or something like that? Right? So it's been modified in modern times to fit the globe narrative. The ball in outer space, which we can debunk very easily. Archimedes' principle didn't have anything to do. Didn't have a G. Go look it up, bro. I gave you the basic testable, repeatable description of what it is. If you want to go into more detail about it, go and learn about it. I'm not going to teach it to you here right now, and I probably can't even get in to the specifics of the actual formulas that Archimedes used. Okay, but it's simple enough, okay, that you can test it right now with an egg and a cup of water and a bag of salt, like I explained to you, and you're going to get the same result every time. You could set it up using, okay, so why anything falls or rises in nature can be easily explained using this principle. And you're not going to be able to give me a single example in nature that goes against it.
Okay.
Okay.
Fair enough. Okay, the next question was, as I said, I had a few questions, right?
Mm-hmm.
So first thing was about gravity. Okay, I understood that. Second was seasons and days and nights. How would I explain
Sure.
that as a flat?
Okay, so we would say that the sun is not 93 million miles away. It's much closer to the Earth. It appears much smaller than the Earth, as does the moon. Okay, and that the sun, we see the sun moving across the sky. Okay, and it moves in particular cycles that reset each year. And that's what creates daytime, nighttime, and the seasons. Okay, so we live within a completely different system than what you're thinking about. Okay, try not to insert the flat Earth inside the globe model, inside the heliocentric model of the universe with a 93 million mile away sun and planets and a big vacuum. Okay, try not to incorporate flat Earth into that system. It's not compatible. It's a completely different way of thinking about this. So we would say the sun is much more local than what we're told. It's much smaller than what we're told. It takes a particular circuit, you could call it, I guess, a particular cycle, just like all of the other, things in the sky, the moon, the planets, the stars, right? Everything is like a big clock in the sky. It moves in cycles. It's responsible for seasons, daytime, nighttime, all sorts of things.
I think we are denying a lot of, a large part of physics here, especially since we denied the truthfulness of Newton's laws of motion.
No, I didn't deny anything. I just told you that when we go out in reality,
Well, they are two
okay, there's
contradicting
no
things.
curvature.
If one is true,
Okay,
then
so
other can't
Newton's
be.
the same person that says the water should be curving, right? Because of gravity. Yeah?
Newton simply said there needs to be a force for things to move. And since I was asking,
Okay, well,
the original question was why.
Newton also said that the water's curving because of gravity. So obviously we can't take everything Newton says seriously.
Yeah, because the water's not.
What part of what he said can we take seriously?
Yeah, hold on. Eternal was trying to say something. Eternal, what did you want to say?
No, I just wanted to say the water's not curving.
Yeah, the water's not curving. That's correct.
Yeah, so you said that we can't take everything seriously what the Newton says, right? So what part can we actually take serious? Because he's a physicist after all. So if you are actually,
I don't know. It doesn't matter. It doesn't matter. You can take
why does it
seriously
not?
what.
It does.
No, it doesn't. Because at the end of the day, when we go out and test the Earth, it's not curving. That's what this conversation is about. It's not digging into every single thing that Newton said and trying to work out which is true and which is untrue.
Then I don't think we can explain why the stone is falling down, because there's no force being applied and without contradicting Newton's laws of motion.
Okay, well, you can test what I said, and it's gonna work every single time. What do you think? What do you think's the reason that
gravity
this? Yeah. What? Oh, so with gravity, the same gravity that would be causing the water to be curved, that's not curved.
I can convince you there. I can't convince on that.
Okay, well, that would debunk gravity, wouldn't it? That would debunk gravity, right?
That would debunk gravity. Then that same thing would debunk the Newton's laws of motion, which is the very basics of physics.
Okay,
and that
well,
would debunk the whole physics then altogether.
Okay, well,
so
I
are we
have
not
empirical
believing in
evidence.
physics anymore?
No. We're believing in measurements and reality. We're not believing in science, pseudoscience. So I have tests, empirical tests that I can show you that show you that the water is not curving, but you don't even
Enlighten
want to
us.
see them. You don't even want to see them because you're not
I've seen
intellectually
them.
honest. No, you
I was
haven't.
I was
No, you've
investing
never
my whole
seen.
day since yesterday about
Yeah,
this
you've never seen
data
any of
topic.
the tests. You've never seen
I
any of
have
the
the
tests that
laser
I have to.
test you were talking about.
No,
The
I
guy
was.
sitting on a
When
beach
did
and
I
putting on
mention a laser
laser.
test?
You
I didn't
did
say
that.
I wasn't going
You
to present
did
a
a while
laser
ago. You
test.
did. You did
No, I
mention laser.
didn't.
Okay, think yeah, fair enough.
Okay, I mentioned
We shouldn't argue
laser
about that.
tests. No, I mentioned laser tests. Okay, but I wasn't going to present that. Okay, you haven't seen all the tests. You might have seen 1 or 2 tests. And in the test you did see, was there any evidence that the Earth is curving?
Well, I also saw a lot of tests that showed Earth is curving.
Okay, which test showed the Earth is curving?
Part of it was the ship sinking down when it crosses the horizon. But
Oh,
you'll just
okay.
say it's reflection.
What's the horizon?
It's the end point that we can see with naked eyes.
Yeah, due to the curvature of the Earth. Is it a byproduct of the curvature?
Yeah, it is.
Yeah, now we're getting somewhere. Now I like the way the conversation's going. So we can calculate the
But
distance.
then yeah,
Yeah, you don't like this because now we're talking about reality.
no, we are going
Right?
on a
Not,
bigger scale. I want to
okay,
start
what
from a smaller
scale?
scale and go there. Okay, okay, continue. You should
No.
continue. Yeah.
Okay, this is the thing now. We're up to talking about horizons and long distance observations.
Mm-hmm.
So you said that the water's curving, and you're saying that the horizon is a byproduct of the Earth curvature.
Mm-hmm.
Do you have any evidence to support that claim?
Simple observation that when the ships go towards the horizon and then when they cross the horizon, the bottom part starts to disappear.
Okay, do you
As
have an example to present that has the variables taken into account?
an example, how would I present? I could present a
Well,
video.
you made the
through my screen
claim.
share.
Yeah, well, you post it in the side chat. You go in the side chat. Control C,
Video
Control
of
V.
it.
Well, you're the one making the claim. Now I'm asking you to support your claim, so we have a side chat where you can post information.
Wait, let me see.
Because we can show things disappearing bottom up on a small scale over a flat surface. Okay, and mainstream optics of light, okay, subject matter experts in optics, okay, they say that things can appear to disappear bottom up, and it's not due to curvature. Okay, it's due to the propagation of light through a medium. This is mainstream
Okay, share
physics
me
of
the
light
document that I could read about because I couldn't understand the thing that you said. I understand the phenomenon that's causing it, but how it's causing it, I don't understand.
How do you understand? Okay, so what's causing it? Tell me. If you think you understand it, tell me what's
I
causing
understand
it
the
and what's the meaning of it. I think
the
you don't
propagation of light
understand
is
it.
causing it. You
Okay,
just
so
said the
how?
propagation of
How is
light
it?
is causing it. For me to better
Okay,
understand the phenomenon, I
can you
have
get
to read
into a
about
little
it.
more detail? Okay, so you don't understand it. Just the propagation of light. So now you agree that things can appear to disappear bottom up due to the propagation of light, and it's not physically obstructed. It's just apparently obstructed. So you agree with that now?
Can you repeat yourself again? I was so
Okay, so you said things disappearing bottom up is your evidence that there's Earth curvature. Okay, things that are beyond the
part of it,
horizon.
yeah.
Yeah, okay, now you're agreeing that it can happen due to the propagation of light.
No, I'm not agreeing to that. I'm saying as you said that, and I want to read why it's happening or how it's happening due to the propagation of light.
All right.
So what can I read about that, and where can I read about that? That's what I was asking.
Okay,
Is there a resource that I could read?
Yeah, I'm gonna drop some citations with links to the original source in the side chat. We can go over them right now. Okay, so just give me a second. I'll just find it.
But explain exactly how Earth is flat, because look at the professor in chat.
Yeah, you go outside and you pay attention to the surface, of the Earth. You just got to ask yourself one question: that when I go outside and make observations, does the surface of the Earth curve at all? If it curves, then yeah, the Earth is a globe. But if it doesn't curve, then how can the Earth be a globe? If you find
I
no
curvature, I sent proof that's.
I didn't make some observations, and apparently we don't believe in physics anymore.
Yeah, so I'm just getting you some citations. So just give me a second.
Yeah. See, curvature is a big deal to justify the globe. You just got to find the curvature, and the Earth is a globe. If you find no curvature, how can the Earth be a globe? Because curvature is a big deal. You do realize that, yeah? When they show you the globe, it's a ball, it's a sphere, yeah? It's an oblate spheroid. The surface has curvature. Curvature is a big deal. And if there is no curvature, how can the Earth be a globe? It's very simple.
All right, so we have exactly great point, T. Yeah, spot on. Okay, so
I think we are cherry picking the physics at this point.
yeah.
Because
So
we believe
no,
some
we're not
part of
denying
physics,
any
but we then
physics. We're
get
talking
there.
about the physics. We're talking about light propagation right now, and you wanted some material by the mainstream, okay, that can explain things appearing to disappear bottom up, but not actually being physically obstructed. Okay, so first we have Oxford Dictionary of Weather. Okay, sinking. This is called sinking, which is a type of low-level inferior mirage. Okay, so here's Oxford reference. A refraction effect in which an object normally visible... You listening?
Wait. It requires me to sign in first to read the actual paper.
Yeah, we've got citations right here that cut straight to the point.
Refraction effect is on which an object normally visible on geographical horizon and the things we need.
Yeah, so I'm going to read them out for you and for the audience that's listening on YouTube and in the channel right now. Okay, so
Live?
sinking.
That's good.
But why
Eternal,
would NASA lie to us
Eternal, you
about
got like Eternal, you got
Earth?
like background noise. I don't know why
me.
why would the government or agencies lie? I have no idea. I think most people aren't lying. Most people genuinely believe that the Earth's a globe. But Eternal, you got like background noises when you're not talking.
That's not me. That's our guy, whatever his name is.
No, that's Arcade's trying to read stuff at the moment. But you got like some. You on a headset or something? I guarantee if I'm. It's okay at the moment. Okay, so Oxford reference. Okay, so sinking is a refraction effect in which an object normally visible on the geographical horizon apparently sinks beneath it. Okay, so it's not actually sinking beneath the horizon. Okay, even though it's appearing to be behind the horizon partially, it's not actually. It's just apparently. Okay, and this is an effect which under the mainstream is classed as atmospheric refraction. Okay, it's a type of miraging effect. It's like a low-level inferior mirage where you have a layer of warmer air down lower and cooler air above it. And as the light comes back off the object towards the observer, it's going to deviate upward towards the cooler portion of the medium because the cooler portion of the medium has a higher refractive index. Okay, and it's going to cause the object in the distance to look like it's sinking. That's why it's called sinking. Okay, and then we have Andrew Thomas Young. Okay, he's like the subject matter expert on optics of the atmosphere. This is from Optics of the Atmosphere Reports in Progress in Physics. Okay, it's got the page numbers there. It says atmospheric refraction can bend light rays such that distant objects are displaced vertically, causing parts of these objects to drop below the apparent horizon or become partially obstructed, even though the line of sight is geometrically unobstructed. Okay, just like the boats over the horizon claim in some cases. Okay, then we got Perkins, David, and atmospheric refraction in geodetic and astronomical observations, surveys in geophysics. Refraction is caused by temperature gradients near Earth's surface. This causes distant land, sea, or urban features to appear distorted or partially visible when they would otherwise be fully visible in the absence of non-such uniform atmospheric conditions. Okay, you could even go on Google right now and type in what is sinking refraction. It's going to say exactly what Oxford reference said up at the top there. It's going to say things look like they're sinking, but they're not actually hidden behind anything. Okay, other times we can have ocean swells, which are waves out in the ocean that can also make things look like they appear to be disappearing bottom up. We can replicate both of these effects that I just mentioned on a small scale on a flat surface. Over and over again, happens every single time. You put the right conditions there, and this happens every single time. So if someone wants to make a claim that a horizon and something that is beyond the horizon is partially obstructed is because of the curvature of the Earth, they're going to have to take these things into account first, and they're going to have to account for these variables to make sure that these things aren't causing what they're seeing in the distance, and that it is actually the curvature of the Earth.
Okay.
Okay, but if I were to
Light.
go up to the moon, take a picture of our Earth, would you believe it?
Yeah, sure, but that's not going to happen, unfortunately. Even NASA, when interviewed recently, okay, they were asked, how come NASA doesn't go back to the moon? NASA said, we'd go back to the moon in a nanosecond, but we destroyed that technology, and it would be a painful process to build it back.
And I bet that's a lie.
Well, that's what NASA said.
But who's saying they're not working with the government, saying that's, you know?
NASA is the government. In fact, NASA
Exactly.
has just been reclassified as a intelligence agency, similar to the CIA or FBI, for example. Right? They can blatantly just lie to people with no
So that's
repercussions.
exactly why. Yeah. So then.
So we can't.
The entire
All I'm
Earth thing.
saying is that we can't go to the moon ourselves and take a picture of the Earth to confirm this. We have to have faith in this intelligence agency called NASA, with the pictures that we're showing us. And then when we see the pictures that they're showing us, and we say, "Hey, look, that water is curving in the picture." Then when we go out and test the water in reality, it's not curving. We have a problem.
We don't know who to believe.
So can I get
The
back
water's
to the
not lying.
reflection part?
Yeah.
Yeah, can I just quickly ask one question? Is that okay?
Yeah, of course, bro.
Sure.
Go ahead.
Sure.
Yeah. Many times I heard people say, "Why are they lying? Why are they lying? Yeah, why governments and scientists are lying?" Look, my point is, yeah, you don't need to question if they're lying or not. You just need to test their claim. That's it, to know if they're lying or not. Do you understand? You don't need to go directly to them
True.
and ask them if they're lying. You can test it, like whatever they're saying, their claim. You can test it yourself in reality.
Yeah, and if I could just back that up, sorry to cut you off there, let me just back that up. Once you've discovered that lie, then it's upon you as to what actions you take. Okay? You know, you have to work it out for yourself.
I agree. Government lies about a lot of stuff you don't even know.
Yeah, I know.
so
We agree.
getting
We can
back
all
to-
agree on that. We can all agree on
Yeah.
that. So, RK, did you have a look over the citations that I put in the side chat?
So I understand the diffraction is causing the light of the ray of light to bend upwards.
Correct.
But when I read more about refraction,
Mhm.
the light bends because when it moves from a lower density medium to a higher density, to the
Well-
change in medium basically.
Well, not really.
So-
That would be referring more to Snell's law, which is the law of refraction, which is depends on a specific situation where you have two different mediums and then you have a sharp boundary layer, kind of like that experiment where you can put a pencil into a glass of water and you can see the pencil is refracting. That's called Snell's law, and that requires two separate mediums. That doesn't apply to a single medium, which is the atmosphere. Okay, the atmosphere and Snell's law, right, they don't go together because you only have a single medium with a gradient rather than two separate mediums with a sharp boundary layer. So you get that kind of like it looks like a band kind of thing in the pencil when you put the pencil into the water. So for Snell's law, you need a specific situation where you have two separate isotropic media with a sharp boundary layer, and then you need as the object, as the light travels from one medium into the other medium, it's going to deviate towards the medium that's more dense.
But Snell's law can work on a gradient atmosphere as well.
No, you would have to use a differential. You would have to use a differential
exactly,
form.
using differential.
Yeah, so but that does, you're not able to use the differential form of Snell's law in the real world observations, because in the real world everything's changing constantly. So you could use the differential form of Snell's law in a lab setting or in a classroom setting or something like that, where you had extremely controlled conditions, where you have a constant gradient, right, that stays the same. Then you could use the differential form of Snell's law. But that doesn't apply when you're out in nature doing observations, because everything's changing. You've got constant shifting of temperatures, pressures, humidity, winds, all sorts of things are taking place. So you're not going to be able to accurately make a calculation using any form of Snell's law through the atmosphere. What you have in the atmosphere. Do you
I
have any
wasn't
problem?
talking about calculations, but actually the direction of the refraction, because since we are on the ocean, above the ocean, the air is actually, it should refract as per the Snell's or gradient Snell's law, using the
No. You see,
differential
I have a
Snell's law.
question. I do have a question. And the question is this.
Bend
Hang on.
the light way downwards, actually.
Yeah, well, hang on. There's a question that has to be asked here, because we're talking about the air. As my colleague has informed you, it's constantly in flux. The gases are in flux. So whilst that's going on, can an object, like in the Black Swan, we have the two oil rigs, can they be lifted from behind a curve up to where I can see them over 10 miles? There's a question there for you already, because that's what you're asking us to accept, that refraction is happening at such a rate, and it's continuous, that it's able to pick up an oil rig from behind the curve that you're supposed to be living on, that ball, and it's lifting it up so I can sit, and it's keeping it there, and I can stand there for 2, 3, 4, 5, 6, 7, 8, 9, 10 hours, still seeing that same thing. What kind of refraction can do that?
Well, yeah, hold that thought, Jin, because that's a great point. But at the moment, we're talking about refraction in relation to what this guy was saying, is that because sometimes we can see things like boats and things like that, they look like they're hidden bottom up. Okay, and then he said that that's proof that the Earth's a globe, because things can appear like their bottom portion of them isn't visible behind the horizon. And I was bringing up some citations showing that there's actually, according to the mainstream, there's effects called sinking that can explain that things that look like they're disappearing bottom up are actually geometrically unobstructed, even according to the mainstream. So you can have like a boat or an oil platform or something like that where you can't see the bottom portion of it behind the horizon. Okay, and even according to the mainstream, that doesn't mean that it's hidden behind the curvature. So then I just shared him some citations where Andrew Thomas Young and Oxford and a bunch of places explain how that works. And then he's looked into that, and now he's trying to wrap his head around that.
Yeah. There's another test he can do. There are two, very quickly, short tests. One is when you're on the streets, walking on the pavement, and you're approaching a manhole cover. That cover, when you don't see it, suddenly something oval shape is appearing on the pavement. And as you approach it, that oval changes and changes as the angle to which you're seeing it at is changing. And suddenly, when you're right on it, it's a full circle. When you back off from it, it starts to change, right? And then you'll get to a point where you'll no longer see that manhole cover, and yet you're on the pavement and it's level. And another one is in a basketball court, where you can take your mobile phone and you place it face down under the basketball net. Walk to the other side of the court where the other net is, lie down, and you won't see your phone. And you're just lying down. You won't see it because the level surface has obstructed. That's not refraction, is it? That's a level surface obstructing what you put down on the floor. It's not until you create an angle at which you can sit. And when you do create that angle, you're seeing your phone as a slither, just a white sliver on the ground. But then when you walk towards it, that sliver changes eventually to the rectangle when you're right above it 90 degrees. So level surfaces can indeed obstruct, and that would include the ocean. I'll stop there. Very good work you're doing there, by the way. Thank you.
We can still see the height of the phone while lying down on the basketball court.
Just the height of what?
He said the I should put my phone at the one end of basketball court, right?
Yes.
And then go back to the other end of the basketball court, lie down with my
Yeah.
eyes
Yeah. You won't see your
in
phone.
line with the flag. I would
You
see
won't.
the light
Yes.
of the phone.
No, you
I
will not.
would.
You will not see. No, you will not see your phone when you're lying down. You will need to get onto your knees before you see your phone.
I would see so you're saying there's
Have
no
you?
depth in
Have
my
you
phone?
actually? Hang on. Have you actually conducted that test? Have you done that? No. So go
I
and
can do
do
it
it,
right
and then
now in
come
my
back and
room.
say I'm wrong. Go and
Yeah, in your room,
do
it's
it,
not going to
and
be
then
long
say I'm
enough.
wrong. Don't tell me. Yeah, that's silly. Go and
It's not
check
going
it
to
out.
be. It's not going to be long enough of a distance in your room. So what can happen is that it's very
Okay, so
difficult.
I can use telescope to see my phone at least. Telescope or some kind of
Look,
magnifying.
look. What my point I'm trying to raise to you, young man, is that a level surface can obscure what you're looking at, and that's one
No, it's
example.
just
Is wait a minute, don't interrupt me because you're not listening and you're just fighting. Don't fight me. Just listen. When you go to the basketball court, put your phone down under the net. Walk to the other side of the court, lie down, and you will not see your phone. Please do that. You haven't done it yet. So don't be telling me no, 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 no. Go and do it first. Then come and tell me I'm wrong. Thank you.
yeah. Thank you for your input. And coming back to the reflection part, can we agree that reflection is caused because of difference in the mediums?
Yeah, so it's caused by the change in the refractive index of the medium, which is
I know that.
primarily controlled by temperature, and the light's going to deviate towards the denser portion of the medium if it's a single medium. Okay, so if you have cooler air down lower, the light's going to bend down towards the cooler air, and if you have cooler air up higher, then the light's going to bend up towards the cooler air. Each one's going to have the opposite effect of each other. This is called looming and sinking.
Exactly. So, when we are talking about the ship sinking, you're saying the higher air is colder, right? For it
No,
to
it depends. It
refract
depends
upwards.
it depends if the heat flux is up or down. So it depends. Sometimes, let's say you have 20-degree ocean water, for example, and you have 10-degree air. Okay, so the warm water of the ocean is going to create a warmer layer of air just above the surface of the water. And then there's going to be a gradient. It's going to get cooler as you go up vertically. Okay, so in that situation, you would have the sinking effect. Okay, and if you had the opposite effect, say you have 20-degree air and 10-degree water, then you're going to have the opposite. You could get a little bit of looming. Okay, and it's only a small difference in the refractive index, a very, very tiny difference, but it's enough to cause these optical effects in the distance. Okay, and we can replicate it on a small scale. We can get a flat floor, right, like in someone's house, and we can manipulate the temperatures, and we can make it look like something disappears behind the horizon on the flat floor. Okay, obviously it's not disappearing behind the curvature. It's just appearing to become obstructed because of the temperature, the pressure, and the humidity.
I see.
Yeah, it's called sinking.
And then in the basketball court, that's called it's an obstruction because of the distance you are and the angle you are trying to look at the object at. This is why it's being obstructed. So what the point we're trying to make to you is that one cannot claim refraction when you're seeing an object at 10 miles, 20 miles, 30 miles. And if you stay there for several hours, it's still there. What kind of refraction is that? That is perfectly set. And it doesn't, we all know that air changes all the time. So there must come a point where I can sit and there's no refraction going on. So you've got to work that out. That's why to claim refraction is really a very poor and weak argument, because the refraction levels are minuscule. They're not able to pick up an object 20 miles away and lift it up so I can see it. That goes against the laws of nature straight off the bat. So, you know, you're going to have to go out and do some more tests to find out, measure curvature is what you have to do. Measure that curve. And you're not doing that because Earth is measured flat anyway. We know that.
Are you there, RK?
Yeah, I'm reading more into it. Just a sec.
Okay, can you have a look in the side chat? I'll show you a real world example of what I was talking about with the sinking. Can you see the side chat?
I saw an image that you just shared.
Yeah, there's a boat. Okay, that's a big giant container ship. It's called the Mandarin Arrow. Okay, so that's the ship that's going to be present in this observation. So this guy went to the beach in the morning and he was able to spot that ship. Okay, that ship was anchored out in the ocean, and here is the screenshot from the ship tracking radar. Okay, so it says that it's anchored and it's 12.4 nautical miles out to sea, which is about just over 14 miles away. So he sets his camera up in the morning at the shoreline, and when he zooms in on the ship, it looks like most of the bottom of the ship is hidden behind the horizon. Can you see this next image that I posted?
Yeah.
Okay, so here's an even closer zoom. Okay, so we can only see the little top bit of the ship. We can't. The whole bottom of the ship looks like it's behind the horizon. Okay, this is the kind of thing people are talking about when they say, "Oh, ships disappear bottom up." Okay, because sometimes we see this effect. Now, if you look closely at that image, you can actually see a mirroring effect right where the horizon and the sky meet. And you can actually see sky, what looks like sky, at the base of the ship. Okay, between the ship and the ocean water. Now, what he did was he actually stayed in that location for the next 3 hours. And he kept zooming in on that ship. Now, what happened was over the next 3 hours, more and more of the ship started to become revealed. Even though the ship wasn't moving, it was anchored, the weather conditions started to change. The temperature of the air started to warm up, and the sinking effect started to go away. Now, 3 hours later, he could see the whole ship 14 miles out. Okay, so this here is the same location. Okay, the same day, the same person, just 3 hours later. Okay, so 3 hours later, we can see the whole ship. Right, there's none of the ship missing now. Showing that what was happening in the morning wasn't actually the ship hidden behind the horizon. It was just an effect that was taking place because of the weather conditions. And it makes logical sense because what happens is the air temperature cools down during the night. The water temperature doesn't cool down during the night. It stays pretty much the same. It might cool down a tiny bit, but the air is always going to get much cooler, especially in some locations. It'll get really cold during the night, but the water will still be warm. Okay, so in the morning when he got to the beach, it hasn't heated up yet. Okay, it's still cold. It's still a cold day. So the water's still warm, and it's creating that warmer layer of air down lower, which has a lower refractive index. And then you've got the cooler air above it. It's going to cause the sinking effect to take place. Now, as the air temperature above the layer of warmer air above the water, as the air temperature surpassed the sea temperature, that sinking effect went away. Okay, so 3 hours later, when we have a much warmer temperature, now the sun's out, it's the middle of the day, and now all of a sudden he can zoom in, he can see the entire ship. Okay, this is showing that the ship wasn't actually hidden behind the curvature of the Earth. It was just what you saw in the citations, right? It matches sinking perfectly. It matches the definition of sinking perfectly. So what I'm saying is most often when you think you can see a ship disappearing over the horizon or something like that, or something that's obstructed bottom up, you need to take these things into account. If you want to claim that it's because of the Earth curvature, right, you need to dismiss this possibility, and then also obviously the possibility of ocean swells as well. Because ocean swells.
So DJ, it's important to point out that this phenomenon never seems to happen where people think it should if Earth is a globe either.
Oh, yeah, that's a great point, actually. Yes, so the horizon should appear closer than it would then it would be geometrically, right? If you had this essentially like negative refraction coefficient.
Yeah, that's why I was mentioning the black swan and that, and 10 miles away you're seeing objects that cannot be lifted up from. That's impossible. That's just not happening. So this is why we call it into question when they keep saying refraction. What type of refraction are they referring to? And then when we're talking about units of miles, one nautical mile or one statute mile, that is a horizontal linear measurement of a distance. It's not curving. You're not measuring curve there. A mile is not 1 mile is not curved. It's a straight linear. Has to be, because as we've said before, Earth is measured flat, and in order for you to determine whether or not Earth is deviating, either convex or concave, you need a horizontal baseline to establish first. This is what we're doing with the miles now. 1 mile straight horizontal, and when you extend it, we find that Earth isn't curving. That's what we flat earthers are finding. We're finding constant horizontality. We're not finding the curvature there. Using the standard statute mile or nautical mile, or if you want to use your kilometers as well. These are linear measurements. They're not curved. Okay? Now you can get a piece of string and wrap it around the ball, but then you're still going to have to lay it down flat to get the actual measurements correctly. We don't have curved miles everywhere, in the sense of measuring, that is. Oh, yeah, well, so TW done a good job there. Oh, no, that's DJ, sorry. Yeah, DJ, you done a good job there. I thoroughly enjoyed what you were doing. The young man hopefully will have some more food for thought, and so do the listeners now, because refraction's often claimed, 9 times out of 10, they're going to claim refraction. And then they have to determine what refraction is that, and then they're going to have to calculate the air quality, the temperature, density, the gases. They've got to do that to prove to us that's what's going on. It's an impossibility, ladies and gentlemen. It's like your fingerprints. The air is similar, constantly changing. You can't measure that. Sorry.
Great point.
Very, very. Yeah. Go ahead.
So when they say refraction is their worst nightmare. As soon as they bring it up, they're done. All of their bottom-up disappearance observations, right? If that wasn't accounted for, that could be what's happening, right? And a refraction effect causing things to appear to sink. Okay, that's an invalid observation now. It's inconclusive, unless they wanted to try to do the impossible and calculate exactly what's going on between point A and point B.
Yeah.
With the refractive index.
It's an impossibility to do that. It's just not.
Well, they could get a rough idea.
I've said, Oh,
go ahead.
I was just going to say, I, as an ex-military man myself, if I had the opportunity to use a weapon, I say to you, get your target down there, set it up. I will hit it. I don't know where you're going to put the target, but put it up. Then I'll find it and I'll blow it up. And I won't be looking for refraction. I'm just going to point and shoot, ladies and gentlemen. That's all I'm going to do with my weapon. I'm not going to calculate the distance, and I'm not going to do that. I'm just going to aim, line of sight, laser beam. We've lit it up, fire, and that will be gone. So it can't be refraction. That's the test that I'd love to do. So when they say it's refraction, it's refraction, is it? Let me blow it up. Then is that refraction now? Thank you, because it's just very annoying all these 10 years that they keep bringing it up, and it's impossible for them to calculate that. And the military don't factor that in when they're shooting at firing their weapons of mass destruction at targets in war events. Okay, they're not calculating for curvature, maybe wind speed, but not curvature. Okay, and definitely not refraction. They don't calculate for that. So just to clarify, I would love to be able to give a test where someone's claiming refraction and we could hit that target, especially on the ocean, where you set it up and we're now seeing it. They said, well, you can only see that because of refraction. Is that right? And then you fire your weapon, boom, and you blow it up right in front of their face. I didn't take into refraction into consideration. How comes I hit it then? If it's a refracted image, I shouldn't be able to hit it. It should be a mirage. That's what a refracted image is. It's an optical illusion. That means I shouldn't be able to see that then, but I'm seeing it. That if I can see it, I will hit it. Now, if I hit it, it couldn't have been refracted. That's the point where I'm trying to make. And those tests need to be done, I think, just to put his refraction silliness to bed.
Well, what about some of the images that DJ was just posting of the ship?
Yeah, those were beautiful images, and those were clearly refraction, of course. You could tell that's right. The thing. Yeah, that's the thing. That's refraction, of course, yeah. But I'm sure if I went to aim to hit that, there would be a miss there. If I aimed at that, that would be a miss. For sure. Yeah, I'm referring to the images like the Black Swan, you know, images like that where we're seeing beyond the geometric horizon, and then it would mean that the object is being lifted up behind from the geometric horizon up to our eyeballs. But that can't be true. If that were the case, then I wouldn't be able to blow it up, but I'm sure I could blow it up. And another point that's overlooked is that how long is this image being refracted for? Because like you can stand at the west coast of California, look at those oil rigs, and you can look at them all day, and they're there. So that's some kind of refraction that keeps it up all day. Conditions don't happen in such a way. Constantly in flux, and as DJ said, as the temperature variation starts to equalize with the ocean, that image starts to disappear. There's natural phenomena going on there. Right. So it cannot be that when I see the oil rigs at 6 miles and 10 miles, that those are refracted images due to atmospheric. No, it's not. Those are the real images. That's what we're actually seeing over that actual distance.
So, RK, most often with the ships, they don't appear like they're sinking. Okay, most often when you see a ship sail out into the ocean, it doesn't disappear bottom up. Most often what happens is the ship will get smaller and smaller and smaller until the optic that you're looking through, whether it be your eyes or a pair of binoculars, can no longer resolve the object due to the angular size of the object becoming too small. Once it gets below 0.02 degrees, the human eye can't resolve it anymore. It's the angular resolution limitation of the human eye. Now, you can't see the boat anymore, but you can still see the horizon because the horizon's giant. So you could think that, oh, wow, I can't see the boat. I could still see the horizon. The boat's gone over the horizon. Well, actually, we can zoom in on that boat and we can bring the entire boat back to view again. Okay, that's on a nice still day where we don't have the effects that we were talking about before, like sinking happening. We don't have the ocean swells. Now, if you introduced some ocean swells, that same boat will look like it's disappearing bottom up, even if there's small ocean swells. Okay, so I would challenge any globe earther to present a single observation where something disappears bottom up, where they've accounted for sinking refraction and they've accounted for physical obstruction, which could be ocean swells / waves. It doesn't exist. There isn't one.
On YouTube, there are distance of 14 miles zoomed in. So you're an individual looking at a ship. It's disappeared from your eyeballs' ability to focus on it. Of course, you can see the horizon because the horizon is much bigger. You're talking of a massive expanse there, bigger than the ship. Remember, the ship is moving away from you, getting smaller and smaller and smaller. Now you can't see the thing. Still there, but you can't see it. So you pick up your binoculars now, take it out of its case, you put it up, focus in, and there's the ship. Now, if it had gone over the curvature, which you think the horizon is, it's the curve there, then I would never be able to see it. It wouldn't be in my view with my binoculars, but there it is. Now, if I keep looking, that ship will disappear from the binoculars' ability to focus on it. Then I would have to take a telescope, which gives me longer range of distance and visibility. And I zoom in there with my telescope, and there it is. I can still see the ship. So when you're working out the time and the distance, there should be X amount of curvature there, but it's not there because the object I'm looking at, although it disappeared from my eyesight, was still able to be visible with my binoculars and then with my telescope. So the question there is, ladies and gentlemen, where is that curvature? Why is it I'm still seeing the ship if we've got curvature going on? Yeah, and 10 miles, 66 feet of curvature should be there, 66.6 feet. It's not there at all. I'm able to see across that 10 miles. I can still see the ship. And then 14 miles, etc., etc. So, you know, there's a lot there people need to take into consideration and digest.
But still, anything that could lead one to think there's Earth curvature is going to be presented as Earth curvature. This includes being able to zoom in at long range on these boats, because the claim is that, well, the Earth is curving, but this is upward looming refraction.
Yeah, and that's why I end up laughing when they say that.
And they'll say that the further down you take your optic, closer to the ground, the further you should be able to see, because the layer of air just above the ground is such that it looms. And so the opposite of what we experience in reality occurs with them. They think the lower that you get, the clearer vantage point you have to distant objects.
Yeah, that goes to show you that they have no idea what they're living on and how Earth works and how nature is operating. They just don't have any idea. We have 14.7 psi at sea level, mean sea level, ladies and gentlemen, where we all live at. 0 level there. That's where we're at. 14.7 psi. And then as you go up in elevation, altitude, the air begins to thin out. So clearly, when we're at sea level, we're looking through the most densest part of the air, where all the factories are, all the ships, cars, traffic, smog, and then you have your early morning dew and everything else going on. So there's a lot to obscure the visibility of what you want to look at through the air. The air will be something that can obstruct what you're looking at also, the air itself, especially at sea level, mean sea level, horizontally looking. If you're looking to the sky, well, there's a difference there because you're looking through the dense, but then you're looking through it as it gets less dense, as you look towards the stars. Okay, but when you're looking horizontally across the Earth, you're looking through the most dense air you could look through, and it will obscure what you want to see over a given distance. Okay, depending on the distance, it'll determine whether or not you're going to have good visibility, and also the weather of that air you're looking through. So if you wanted to look through, let's say, 2,000 miles, 3,000 miles, as some of these globers think you can, why can't I see Paris from New York? Well, the reason you won't be able to see Paris from New York is, one, the distance, and then within that 3,000 miles, you've got to consider the weather systems between New York and Paris. Okay, there's weather systems there. Sunny here, but raining over there, for example. That's going to obscure. So the distance and all that air will turn, it just gets more and more opaque the further you look across. So it's not possible to see that. Impossible.
More importantly, did you just call Paris Paris?
Well, yeah, that's French, gay Paris. Eh?
No, okay, fair enough.
Oh, he's a spy.
Nice one. Happy New Year to you, sir.
Happy New Year, brother. Good to see you.
Yeah, Jedi. The French call it Paris, don't they? They call it gay Paris. They don't say Paris, as we say in England.
It's like, I've noticed this since the Ukraine war. We used to call Kiev, because that's how we say it. But now all of the news announcers and throughout the world, everyone's pronouncing it Kiev. So that means an instance, then we've got to call Paris, Paris, like you just did.
Yeah. But I still call it Kiev. And when I want to eat a chicken, I don't say chicken Kiev. Can I have a chicken Kiev, please? Do you know what I mean?
Yeah. We're supposed to go around going New York with the accent all the time. As long as we say place names, we have Say it with the accent. I like it.
Yeah, yeah.
But good morning, everybody. I hope everybody's doing well. I say good morning. It's actually afternoon. I slept in a little bit today. I hope everybody's doing well. It's raining outside. Winter is so bloody miserable in the UK. But I hope everybody else is experiencing maybe some better weather.
Dude, it's so cold here. It's like negative 12 here, and I went out to start my car and it wouldn't start because the cold drained my battery.
Your car just turned around and you went, fuck off, it's too cold.
Yeah. I held the key. It's like turned. I'm like, it's going to start any second. And then the battery just stopped working.
No.
Yeah.
It's out there buried in snow.
DJ, do you not have a battery charger at home?
Yeah, we got a battery charger. Yeah, I got to hook it up to the charger.
Right. So basically, in winter time in particular, you need to do that at least, twice a month. If you're not doing the mileage, then you do that twice a month. So every 2 weeks, just give it a little bit of a charge. Only through, let's say, your cold months. Let's say like maybe December, January, February. Those 3 months in particular, and then that's it. Then you'd be okay with your battery.
Yeah. I guess I learned the hard way.
Yeah. But yeah, I know that back in the old days, motorbikes wouldn't start in the winter, especially old British bikes. But the way to solve that was to remove the spark plugs, for example, and then put them on the gas cooker. So you heat them up, literally cook them on the cooker, and then wrap them up in a cloth so you don't burn your hands. Run back out to the bike, plug one in first, and then put the other one, and then the bike would start because the spark plug had some heat in it.
Oh, wow.
See that? Yeah. Yeah, that was only with the British bikes. Japanese bikes never had that problem of starting up in winter. All the cars, they start up all the time. But British bikes, they seem to have a problem with the winter, and it wouldn't start up. But there are times when you just do that, use that method, and yeah, good as gold. Boom, and where you go.
I've got one word for you, DJ. Gold rush.
Oh, I've watched some videos on that before. I need to brush up on that. Well, I have, but I don't remember it very well. Definitely interesting. Yeah. I remember what I saw was interesting. What did you watch?
Kind of just some kind of reclamation event, as in shit goes down, everyone can't live there, and then they spend like 50 years going back over old ruins and stuff and pulling out all of the ancient technology, melting it down and turning it to gold.
What? Whoa.
So the gold rush in America, right?
Yeah.
So not going into mountains to pan for gold, going into cities to try and pull out the technology that was buried underneath the mud and the rubble. So not panning for gold, reclaiming gold.
Interesting.
I mean, I don't know, do that.
Yeah, because it does surprise me, when they have these seams of gold, veins and seams of gold, and you think, how did Earth make that, but not make the whole rock? Only that little vein. You understand? Because that's what they talk about when they're actually panning for gold or drilling and digging for gold. They're looking at veins all the time. Strange. What happened for that phenomena to happen to make the gold? What happened? Strange.
But yeah, just been coming across a lot of interesting subjects recently that I'd never even considered asking about.
Yeah, it's a trip, isn't it? Yeah, me too.
It really is,
I can't wait to watch some stuff today. Actually, I'm about to log off and watch some stuff while I work. So it'll be all of that old world stuff for sure.
Good shit, dude. I did watch a really interesting one yesterday with regards to the education system in the early 19th century. How it was implemented, what was and what was not taught, for example. Yes. At the same time, the education system changed at the same time that there were lots of children being moved around the earth, so like the orphan trains and so on. So the education system looks like it started as re-indoctrination camps.
Yeah, if you could send me a link to that, Jedi, I would be really thankful. Okay?
Yeah, man.
If you could
No worries, dude. Yeah, no worries.
Yeah, wicked, man. Wicked.
Yeah, man. If you're handing out links to that, I'd definitely take one. It sounds like a good watch. I'll watch that first.
No problem at all. But what's the vibe been like in here today? Anything interesting been going on?
Yeah, I was having a pretty long chat with this guy RK. Started off with gRaViTy, and then I sort of switched it over to if gRaViTy were to exist the way he was explaining it, or how it would be explained on a globe, then the water would have to be curving. And then we sort of got into long distance observations and horizons and that kind of thing. And then it was towards the end of that you came in.
Yeah, such a great learning curve that was. Pun intended there, ladies and gentlemen, because you don't get any curve out there in reality. But, you know, as is the year 2026 is the year of the horizontal constant. But that was a great learning curve, what DJ did there. I had a little bit of an input, but 90% and 95% of work was done by DJ earlier. It was good. Oh, yeah, definitely. Good one for the people who are listening. Because, you know, because you're jogging, you're prompting them to question. You see what I mean? That's what's good about it.